Okay, so let's begin. That's just a picture of the apparatus. Of course, you don't need to jot that down. It's more than anything, it's for me, when I'm looking for files, I recognize what it is. Okay, so some preamble, some sort of what we're going to do here. Okay, so what we're going to do is we're going to take the results of our experiment, derive some formulas that relate centripetal force Fc to various aspects of UCM, and you will note actually that one of the outcomes is to do an experiment where you do this. So check, done, right? So the first thing we did, you should have graphed period squared versus Fc, and when you got it, your graph should have looked like this, and if you haven't graphed it yet, this is what it should look like. Is that what it looked like? Sort of, kind of? As the period goes up, as the centripetal force goes up, as the number of washers goes up, the period should have gone down, which meant that it went faster. If the period goes down, that means it's going faster. Period is how long it takes for one revolution, and it was period squared. Okay? So this suggests that this may be an inverse or inverse squared relationship. Back in the long time ago days, before we had computers and graphing calculators and such, to find out what a relationship is, you had to sort of graph it and then adjust your equation and hope that you ended up with graphing a straight line. Okay, so what we're going to do is you graphed, I asked you to do this, we graphed t squared versus 1 over fc. And if you get a straight line, then it tells you that it is a inverse squared relationship, because we've got t squared here. And then when you did that graph, you should have got that. Did you get kind of squared, kind of straight-ish? Most of the time, kids get reasonable results here. Okay, because again, we're not really looking for numbers, we're looking for relationship. So this suggests then that t squared is proportional to 1 over fc. Okay? In other words, as the centripetal force goes up, because it's inverse, the period squared goes down. They're opposite. Inverse relationship, right? As one goes up, the other goes down. Another inverse relationship. The more your absences goes up, the lower your mark goes down, in general. Just saying. I don't need to say that to you guys. You guys know. That's more for the grade levels. What about period squared versus radius? What did you find? In part B, as you adjusted the length of the circle, the radius, what happened to the speed? As the circle got longer, the speed should have got slower. And when the speed gets slower, the period goes up, right? So as the radius went up, the period should have gone up, and you should have gotten a straight line graph. And so those of you who are still in the process of doing this lab, that's the graph you should see. This tells us that period squared is proportional to r. As the radius goes up, period squared goes up. All right, and in part C, when we were adding rubber stoppers, what happened to the speed, Austin? As we added more and more rubber stoppers, what happened to the speed? Remember? I know it's a few days ago. Anyone remember what happened to the speed? Josh? It got slower, and if it gets slower, then that means the period goes up or goes down? Up. So in other words, the more mass, as you increase the mass, right, as the mass gets bigger, the period should get bigger, right? This implies that t squared is proportional to m. So what we've done is we've got three relationships now. We've got t squared is proportional to m, we got t squared is proportional to r, and we got t squared is proportional to 1 over sc. Can you combine all three of those into one big giant mega proportionality? The answer is yes. So by combining our proportionalities together, we get the mega proportionality statement. T squared is proportional to Rm over Fc. Excuse me, I get a little choked up about this. It's pretty emotional. As an equation. Now, I don't know if you've ever been shown this or not. Briefly alluded to in grade 11 when we did the circles lab, right? How do you turn a proportionality statement into an equation? Well, you change the proportionality statement with the equal sign, but you also have to bring in what's called the constant of proportionality. Okay, so t squared is equal to k is your proportionality constant, Rm over Fc. So you replace the proportionality statement with an equal, and you throw in a k, right? And we use the letter k for constant because the letter c is speed of light constant, special constant, it's taken. So we use k for sort of a generic one. Okay, so k is called a constant of proportionality. What number is it? 6, 42, pi? That remains to be seen. Do you have a funny feeling that pi might be involved, given that we're talking about circular motion? Likely, right? You probably have an idea that pi is going to be in there somewhere. Okay. And of course, we can rearrange this. We're going to flip the Fc and the t squared. We're going to rearrange this to this. Okay? So what I'm saying is that based on our lab and the results that you all got, this is the proposed equation for centripetal force and its relationship to radius, mass, and period squared. Okay, that's our proposed equation. Now I'm going to do some fancy algebra to prove it. You will sit in awe. If you compare this to F equals ma, the old Newton's laws stand by, right? If you compare this to F equals ma, I got F on the left, I got F on the left. I got m over here on the right, I got m on the right. So what is the value of AC? What would it? I heard someone say something. Right? Here's the m. Go ahead, Sean. You're right, I'm sure you are. Kr over t squared. We're going to predict then that the formula for centripetal acceleration is Kr over t squared. This is our predicted formula. And again, as I said, I'm going to do some fancy algebra, and we're going to come up with this. Okay? But I want to point out that these are things that you can come up with if you know what you're doing from the lab that you did. Okay? That they're not just magic. They don't just come from, magic beans. Traded for a cow. Thank you. Yes, I can remember.
The cows really worth that much?
I don't know.
3 magic beans.
Depends if they're actually magic or not. I know, but when you make that trade, you don't know. We're going to attempt to derive a formula to see if it matches our prediction, and we will determine the value for K. All right, I can sense the apprehension and the excitement in the air on this Monday morning. All right. I'm not going to say you have to write it down. You might want to do like synopsis of stuff. Okay, so we're going to talk about speed and period. In one complete revolution, the distance traveled d, as you go around the circle, the distance traveled d is the circumference. And we know the formula for circumference is 2 pi r. That's probably something you learned about grade 7 or 8, I think, right? Hopefully. 2 pi r. This time, the time is the period. Now we use capital T for period. That's a special time. Yes, it's a special time in your life. Given this, we're going to write the formula for speed, and we're going to substitute. So speed, or velocity, is distance over time. What's the distance traveled? Circumference. What's the time? Period. In other words, v equals 2 pi r over t. And then we're going to rearrange that. We're going to flip the v and the t, and we're going to come up with t equals 2 pi r over v. And I'm going to put a box around that because I'm going to call this saved equation number 1. We've derived this equation from our basic geometry knowledge. And I'll pause there for dramatic effect. And let's talk about centripetal acceleration. We know that the formula for acceleration is a equals delta v over delta t. We're going to rearrange this to delta v equals a delta t. for one entire revolution. Delta t, the change in time, is the period, and delta v is delta vt, and I'm just going to subscript that, delta vt, total change in velocity for one period. Okay, so for an entire revolution. Is there a problem? Okay, so all I'm saying is that in this particular situation, delta t in the generic formula is the period, and delta v I'm just going to relabel as delta vt. In other words, total change of velocity for one singular period, one singular rotation. Okay, and then this gives us delta vt is equal to a times t, and I'm going to call this saved equation number 2. Why am I saving these equations? We're going to use them later. We're going to kind of put them together, Lego style. Yeah, actually nothing at all like Lego. Okay, here's the crazy slide that I always have to come in 5 minutes ahead of time and remind myself how it works. But I've done a pretty good job of laying it out, and it used to be a whole lot worse for me. Okay? Another way to think about delta V for a whole revolution. Okay? Suppose several instantaneous velocities recorded, and these are shown as tangent lines below. Okay, so look at this here. Right? Here's my circular motion. And at various points around the circle, I draw the instantaneous velocity, which is a tangent line, right? Because if I let go, right, remember with the whole me flowing under Bailey kind of thing, right? If I let go at that point, it's going to go flying to the left, right? And would you agree that all of those vector lengths should be the same length? Why should they be the same length? Because it's traveling at constant speed. Martin, you should be watching, not. All right. Each vector, vector 1, vector 2, vector 3, is the same length because the speed is constant. Now, this value delta v is the difference between v1 and v2 and so on. So if you think about this vector here, to there, and those should actually be the same length. It depends on how well I drew them. But those red ones there are the change in velocities. How much the velocity changes. Now, if you place v1, v2, v3, all the way up to 8, like if you take all these black ones, and instead of putting them on the circle, if you place them like so, whoopsie, wrong one. If you kind of go around the horn here, and you place them all, and those should all be the same length, by the way. If you place them all tail to tail, that's another way of geometrically showing vector subtraction. And if you do that, well, then you get something that kind of looks like this. Do you see that? Right? So this would be like V1, V2, V3, and all the way around, right? And then delta V1 and delta V2 and so on are now these red ones here. Okay, now, here's sort of a calculus concept. I didn't feel like drawing more than 8 vectors. I think you get the point. But if I were to draw, say, 16 of them, what would the shape of the red figure be like? More circular. And if I were to draw, say, 100 black vectors, the red ones would be virtually circular, right? That's sort of that idea of a limit. As you do more and more, it gets smoothed out, kind of thing. That's kind of the calculus concept. Well, each one would be a single degree of, right? Exactly. Okay, and in computer science, that's what we do, right? We make a 360-sided figure to make a circle. Exactly. Okay, so in this case here now, the total change in velocity, delta Vt, total change in velocity would be delta V1 plus delta V2 plus delta V3, all of the various red vectors. As many as you want, right? And because it's a circular shape, that delta Vt would be 2 pi r, circumference. What is the value of r in this red circle? Circle, air quotes. What is the value of r in this red circle? The black ones, right? Which is V1, which are all the same, where r is V1, V2, V3. So 2 pi r becomes 2 pi v. Delta Vt is 2 pi v. Saved equation number 3. What's the point of all this? First of all, Do I expect you to do this on the test?
Yes.
No. No. Okay? I don't even expect you to get every single point along the way. The big idea, the main thing here is formulas don't just come from magic. There's logic behind them, right? And I've introduced you to that several times. This is probably the most complex. I got three saved equations, right? Do you kind of have them sort of on your paper somewhere? Do you see something that is similar between all three of them? They all have a 2? Do they have a common letter, Martin? Yeah, they're kind of various common letters, right? You get the feeling we're going to be able to put them together somehow. Okay, there's a relationship. Excellent. Okay, so let's go back and do this. Recall equations 2 and 3. Delta VT is equal to AT, and delta VT is 2 pi V. Are both of those delta VTs the same? They are. In other words, I can make this equal to that. Right? Giving us AT is equal to 2 pi V. And if you prefer, you can rearrange that to A equals 2 pi V over T. Right? Just divide both sides by T. Saved equation number 4. We are proposing geometrically that the centripetal acceleration is equal to 2 pi V over T. Don't worry, when we're all done, I'm going to give you the formulas, the ones you need to know. Don't worry. Go back to saved equation number 1. Saved equation number 1 said that T was equal to 2 pi R over V. Is this T and that T the same?
Yeah.
Guess what I'm going to do? Is that going to be a really ugly fraction? You betcha. But do you see that it's going to be 2 pi V over 2 pi? We might get some canceling going on here, right? We're going to substitute equation 1 into equation 4 for T. Okay, so, all right. So I've got this 2 pi R over V, and I'm going to plug it in there. That's basically that line there is just what I said I was going to do, right? Which gives us, let me just cover that up over there. Well, anyways, it's going to be 2 pi V all over 2 pi R over V. Don't worry about this stuff over here on the, don't worry about that. And what do you get? You can't cancel, the 2's cancel, the pi's cancel, and you end up with V over R over V. V over R over V, and the V can go up top, and you end up with AC is equal to V squared over R. Well, that doesn't sound so bad. Centripetal acceleration is equal to V squared over R. Now, if we go back, I'll come back to this slide, don't worry. If we go back to way back here, is this anything like our one that we just came up with? We predicted from our relationships, from our graphs, that we were going to get KR over T squared. Here we got something not all close to that, right? Okay, now I've got something over here as well, up my sleeve. Could you say here that, can you take this formula right here and just pull the V off and multiply after? Like when you go 2 times pi times V divided by T, could you also go 2 times pi, divide by T, and then multiply by V? Order of operations, that works, right? So all I'm doing is I'm pulling the V out, and I get 2 pi over T times V, right? And V is equal to, from over here, if I take that V and that T and flip them, you're going to get 2 pi r over T. I'm going to take that V and I'm going to put in 2 pi r over T, multiply. And how do you multiply fractions? Straight across. So 2 pi times 2 pi r is going to be 4 pi squared r all over T squared. Notice that those are in boxes. You need those ones. These are the two that you need. 4 pi squared r over T squared. And you will recall me saying at the start of this nonsense that do you get a feeling that pi is going to be in these formulas somewhere? And sure enough it is. Now I want to point out a common mistake here. Go ahead. I want to point out that way back in about grade 7 or 8 you were taught area of a circle is? Come on. What's the area of a circle? No. The formula for area of a circle. I know it's Monday.
No, I don't remember.
Oh. Pi r squared. Is it not pi r squared? Pi r squared. What is this? This is 4 pi squared r. Countless grade 12 students have gotten this wrong because they just go 4 pi r squared. Right? Because that's just kind of what they've used that before, right? So be very careful. It's 4 pi squared r over T squared. Now, let's look at this and go back to that predicted one that we had. Kr over T squared. Oh, that looks similar, doesn't it? Let's just put them side by side. Does that look similar? It sure does. In these formulas, of course, v is the velocity in meters per second, r is the rate of circle, must be in meters, a is the centripetal acceleration, which is in meters per second squared, and t is the period in seconds. Now, given these two side by sides here, what's the value of k? 4 pi squared? Oh, I got ahead of myself here. What was our predicted formula based on the experiment? And we derived this. What is the value of k? You're right, 4 pi squared. So I want you to realize that what we did was we took those relationships that you came up with from the lab, from the graphs, and we massaged those into a suggested hypothesis or a proposed equation, and then we did some fancy geometry, and we got something that matched, and their value of k is 4 pi squared. Now that's interesting that it works. Did we ever weigh the stoppers? No. Our unit for mass was number of stoppers. Our unit for centripetal force was not newtons, it was number of washers, right? Did we have to measure the length of the string in meters? No, we just did because it's convenient, right? So I want you to realize that these things can come up with regardless of the units, because we were talking more about the relationship. Can be stuff for a Monday morning. I'm nearing done. Are you staying with me? Okay. Given our formulas for A, which we just came up with, v squared over r and 4 pi squared r over t squared, if you want a formula for centripetal force, and you will, remember Newton's law, which says F equals ma, and if the F is centripetal force and the A then is centripetal acceleration, how do I make these equations for acceleration into ones for force? What did I add here? Am I not just adding a mass? So in other words, do what? Stick a mass in those formulas. So we simply add m to the formulas to turn the A into an F. Okay, so if I want the A to become a F, then I have to put a mass in there. And if I want this one to become an F, is this making sense? I have to stick a m in there too in the front. And so in other words, Fc is equal to mv squared over r. and FC is equal to M4 pi squared R over T squared. Now, is that not the most beautiful formula you've ever seen in your life? I sound like Don Cherry for a second. Think back with a little nostalgia, if you will. Some of you were shown the magic triangle in maybe grade 9 or 10. Anyone ever see those? Okay. This is why, I don't know if my reputation precedes me or not, but this is why I hate the magic triangles. Because if all you know is the magic triangles, good luck trying to apply it to this. Right? You're going to need like a magic pentagon or something. Okay? Oh, that wouldn't be fair, Shane. Okay? So those are our formulas. FC is equal to MP squared over R, and FC is equal to M4 pi squared R over T squared. It's a mouthful.
Ha 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 ha. Ha 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 ha. Ha ha ha.